Okay, welcome everybody. My name is Jesse Hoy. I'm a professor here. I'm going to introduce President Chan, who we're delighted to have here from the King Abdullah University of Science and Technology, where he has been the president since September of 2018, after nearly a decade as the president of the Hong Kong University of Science and Technology. Before joining the Hong Kong University, President Chan was Assistant Director of the Mathematical and Physical Sciences Directorate at the U.S. National Science Foundation from 2006 to 2009. He taught computer science at Yale University before joining UCLA as a professor of mathematics in 1986, and was the chair of the Department of Mathematics in 1997 and later Dean of Physical Sciences. He was co-founder and director of the U.S. NSF-funded National Math Institute, IPAM. He received his Bachelor and Master's of Science degrees in engineering from Caltech, where he told me before starting that he took physics classes studying Richard Feynman's notes, and that was one of the reasons Caltech was so appealing to him. And he got a PhD in computer science from Stanford University, where our dear friend David Cheriton began as a professor just the year that President Chan left. And this was followed by a research fellowship at Caltech, and he holds an honorary doctorate from the University of Strathclyde in Scotland. And he is a member of the U.S. National Academy of Engineering, a fellow of the IEEE, AAAS, and SIAM, and he was awarded the 2020 SIAM Prize for Distinguished Service to the profession. So, Professor Chan.
Okay. Well, thank you very much, Jesse, for the kind introduction. Let me, before I get into my talk, say a few personal notes about this thing. First of all, I'm extremely honored to be invited to give this distinguished lecture. Waterloo, in my mind, has always been one of the best universities in the world. I'm a tech guy, okay? And so that's one thing. I'm extremely honored. And second thing I want to say is, in my conversation with Jesse, I was asking, you saw in my bio that he mentioned, I was chair of math, but I also taught in computer science department. I wanted to be a physicist. All that is true. So I was asking Jesse, I said, I'm getting an honorary doctorate tomorrow in math, but I'm speaking in the School of Computer Science. How did that happen? Okay. Then he explained to me, because there's a faculty of math. This is actually a very interesting structure. I think it's unique to Waterloo in some sense. So I don't have a degree in math, okay? But I'll be talking about computational math, okay? I've learned in life that it's not what degree you get you are in. It's basically what you have done or what you do that matters. So that's the most important thing. My connection to Waterloo is it goes back a long way. Goes back a long way. I know Alan George is here. Where is Alan? Yeah. I remember very well, 1984, my first visit to Waterloo. It was because of Householder Symposium that you organized, right? Am I right? It was in 1984? Yeah, I remember my first visit to Waterloo. I still remember, that was, you guys know MATLAB, right? You guys, now it's a big company. Sorry. Back then, I remember during that meeting, it was the first time, it was in Fortran, first of all, and then the first time that it can make plots. I still remember Cleve Moeller showing us about that MATLAB can make plots. It was a raster plot, so on. But now, of course, there's 1,000 people working there, a $1 billion company or something like that. So since then, of course, I've come many times. The last visit I had was 2018. I know President Sheridan rather well, just overall. And in fact, I had breakfast with him this morning, and we were reminiscing about all kinds of stuff. So my connection with Waterloo goes back a long way, also through the people that I know, like Alan, Sheridan, and so on. So let me, oops, what happened here? Okay. Yeah.
Now, they're having some other issues.
Okay. Thank you. So I have about 30 slides or so. This is not a technical talk, because you can see it's very personal and historical. You know, sometimes with age, it gives you a different perspective on the field. So I'm speaking, there's not meant, there are only a few equations in there, okay? So I don't pretend to be up to date. You know, I was, since I became president of CAUS, I decided I'm not going to be active in research. I want to make sure that I do my president's job 200%. That's what I'm trying to do. So take that keep that in mind, please. So let me go to the first slide. So it's not the first time I gave this talk, but it's a talk that I constantly update. My thinking changes, and you see some of the detail change. So first thing, I want to find out what's the definition of computational math. Because I went into it, I went to study computer science at Stanford, as you heard. Okay, of course there was a group. They're doing numerical analysis. It's called, that's the group that Alan was. We never overlapped, but we belong to the same group. I didn't know what it meant. You know, I studied all the other computer science things, complexity theory, you know, P equal to NP, and all this other stuff. Artificial intelligence, which is completely different from what it is today. So I stumble into it. It's just what I do, okay? What I've been doing. So this is the definition. I don't have to read it out. But historically, there are actually many physicists and mathematicians who are actually leaders in this field, starting with Newton. I mean, Gauss, Richardson, you know, weather forecasting, von Neumann, obviously, you know, so, and so on, many, many, many. So that's the definition of computational math, okay, where basically both computing and math plays a central role, okay, in application to other areas. The modern history, in a way, I call the modern history started at the end of actually during the Second World War, because of, you know, the enigma and so on. But really started after the Second World War. In fact, UCLA was one of the birthplaces. I spent over 20 years at UCLA. It's an interesting story. I would give you a little tidbit of it. There was an Institute of Numerical Analysis at UCLA between 1947 and 1954. Richard Feynman was a member, I remember. So the story is, after the Second World War, the US government realized that computers are actually very important because of the war. So they want to keep that going. And the National Bureau of Standards, NBS, now it's called NIST, National Institute for Science and Technology, I guess. So they are based in Washington, D.C., obviously. But they said, no, this is a new thing. We want to set up this thing in a new place. So they picked Los Angeles to set up this new institute, okay? So they funded it for about 10 years or so, you can say. And then at the end, it was closed down. Why? Because of politics. Because they published something on about car batteries, or batteries in general. Somehow offended some people, okay, who then lobbied with the government and said, you got to close down this institute. And it was closed down. It had some brilliant people. Some of you may know, like this method called Conjugate Gradient. Some of you may know. It's actually used by, the paper was 1952 by Hestenes and Stiefel. So Hestenes was a professor at UCLA. Stiefel was a professor at ETH in Switzerland. They did not work together. So Stiefel was visiting this institute, gave a talk, and then Hestenes said, oh, this is exactly what I did. So they wrote a paper together, which is very influential. That's where this institute can be very, very useful. SIAM, just as you were asking me, right, it stands for Society for Industrial and Applied Math. It's certainly in the US, but globally, it's become the main professional society. In fact, it was founded in 1952, about the same era. So a number of journals, and many of us, conferences and so on. And I would say the modern description, the era of algorithm was founded about that time. There are many computational math algorithms were founded about that time. I mentioned some of these: successive over relaxation, conjugate gradient, alternate direction, implicit method, simplex method even. It was around there. George Danzig was working in RAND and so on. So LA was kind of like the mecca of algorithm. I should divert a little bit. You know, algorithm is an Arabic word. I didn't realize this until I went to KAUST. So the building I look across the window is algorithm building. It's Exactly. Who said that? Yeah, exactly. So we have a museum where we exhibit his stuff. It's interesting. We all know that I knew algebra is an Arabic word, for example. Alcohol is also an Arabic word. Okay, so anything that starts with AL is almost that. So I say that because it's probably pre-Islamic, I think. Am I right? Are you Arabic? Are you? Yeah. Okay. So a little bit more about myself because I'm talking about personal history, right? So a little bit more about myself. So I was an undergrad at Caltech. I was studying all the classical applied math stuff. I would say the British style of applied math. If you don't understand that stuff, it's okay. Perturbation analysis, WKB, all the transforms, game theory. I studied numerical analysis from Isaacson and Keller, from that book, for example. I was a postdoc for Herb Keller. So some of these you see from there. The first computer I used was PDP-11, paper tape. Then you have batch like IBM 360s. I used the first version of the HP35C, $400 US, I remember. Back then, it was a miracle at that point. HP 2000, you program by flipping switches. Okay, it's like flying an airplane. Poop, poop, poop. That's how you program it. I was one of the first users of ARPANET. There was only maybe less than 50 people who used the ARPANET. And there's one, what's called Maxima. You probably know, Jesse, you probably know about Maxima. You work in symbolic computing, right? Oh no, somebody else was, not you, maybe. Yeah, so there was one Maxima, one version sitting in MIT. Those of us who use it have to log in. So there was sort of the ARPANET. You log in, maybe there are 2 other people on that computer. And so I sort of went through all that. So the software I use, you see the algorithm I've used, you can see it there. So that's sort of my upbringing in computational math. Now, in terms of my own research, I work on a number of things. This is a large variety, but it's driven by my interest in using mathematics and computer science techniques to move forward methods that are used and understand the physical world. That's really what it is. In fact, it touched a lot on engineering. So, for example, I worked on nonlinear PDEs, numerical linear algebra, multi-grid method, domain decomposition method, and later on I work on VLSI, brain mapping, image processing, and so on. But they look like a potpourri of different topics, but they all have the same underlying methodology. In linear algebra, I work on, you see there's an advent of this. In fact, this is a householder symposium that Alan organized, 1984 in Waterloo. I was very much involved in organizing the series of domain decomposition meetings. They're still going on today. I sort of left some time ago. There's a whole slew of, supercomputers, cosmic cubes, connection machines. By the way, COUS has one of the fastest university-based supercomputer in the world. So we are very much involved with that. Packages, MATLAB, as I saw it, before MathWorks. In fact, some of us know this year's Turing Award winner, Jack Dongarra. We know each other from way back. I'm very happy that he won because, in a way, it sort of gives recognition to high-performance computing and numerical software, for example. Okay, so I think that's very important. So now I want to say this. As I said, I do not have a degree in math. And throughout my career, I felt that there's some areas of math that I should have learned, but I didn't. And it's very difficult to learn while you're doing the research. Okay? So here's some of the things that I should have learned. I've since used them in my own research. I really should have learned it in school. So let me start by putting up the latest top 500 ranking of supercomputers. That just came out a few weeks ago. Okay, and this list is published every 6 months. Okay, this is the latest one. I basically updated a few days ago. So this is from the US in Oak Ridge. This is from Riken in Japan. And Finland, I didn't know this. Finland has 5 million people? So So this is I didn't know anything about this. This is also in Oak Ridge. And so most of these are in the US. I can tell you one thing. The last one, 6 months before, this was number one. And this doesn't exist. I think this summit was number one maybe a year or two ago. So this is like a race. It's like the Formula One race, It's Mercedes and then Ferrari and then now it's a Red Bull and whatever is going on. So the next one, is number 6 to number 10 is this. There are 2 from China. These 2 were both number 1 some time ago. In fact, if you look at the news media says China actually has 2 other computers that would have been higher on the list. They decided not to submit it because they didn't want to cause political problem. I don't know. But this is in the Western press. This is in the Western press. Okay, so this is Berkeley and so on. So what we hope is that we will acquire Chaos, a supercomputer that will be somewhere in maybe not the top 5, because those are national systems that cost literally several $100 million a piece. Okay, but we will be doing this. So this has really come a long way. In fact, this is the first exascale supercomputer, first. Exa is 10 to the 15 or something, I forgot what it is, exa. So it's the first time that you could have that. Yeah. Okay, so that's supercomputer. So here's something I follow. I think in fact Jack Dongaro was one of the co-authors of this. In the millennium year, in the year 2000, there was this magazine called Computational Science and Engineering, I think published by IEEE. They published the top 10 algorithms. Of course, if you ask 10 different people, you'll 10 different answers. But this is from them. So you see the list there, okay? And I was checking every few years, I check whether there's an update. No, there's no update as far as I can tell. So if you look at this, you can agree or not agree with it. I mean, I myself have used quite a number of them. Basically, except for integer relation detection, I think I've used all of them myself. So, okay. So then there are other new algorithmic paradigms that has come up since 20 years ago, 22 years ago. Multi-level methods is one paradigm. It's not just in solving partial differential equations. For example, convolution neural network is really a multi-level method. If you look at it, right? It's just graph-based rather than based on a grid. It's a graph. Domain decomposition was first developed in the Soviet Union when it was still Soviet. And the motivation was they are lousy computers. Their computer have very limited memory. So you have to make use of the limited memory to do large-scale computation. And so you break down the problem into little chunks. You solve the little chunks and put them together. That's domain decomposition. So that was, sometimes you can be spoiled by good hardware. You don't think hard enough. You just go straight. So multi-scale, I mentioned. Uncertainty, that was a new development. Now I think SIAM has a journal on uncertainty quantification, I think it's called, and all this. So the idea is that it's not enough to just do a deterministic prediction, because you don't have, the data has uncertainty. The model, the physics is always probabilistic, so you need to sort of build that into your computation. And then there is this thing that I've actually lived through myself. When I was studying computer science basically had an identity crisis, I would say. I was a student, I can say that, right? So the idea is that anything continuous, that's not computer science. That's the math guys. We do graph, we do discrete stuff, okay, symbolic. Well, today, if you look at machine learning or anything, right? It's just whatever works, that should be the attitude. So, but this idea of differential equation versus or continuous versus discrete is all gone. But back then, it was the main divide. So 2021, deep neural networks. So everybody is doing deep neural networks. I can't think of any single field of science and engineering that's not doing this. Okay, you can be a material scientist, you could be a chemist. Certainly if you're a computational mathematician, I will have a few more slides on that. You're doing this, okay? So everybody looks at it differently. So for someone in, say, optimization, well, machine learning is just optimization. In a way it is, based on data and so on. In a way, someone working on multi-grid or domain decomposition say, well, it's only another example of multi-scale method, which in a way it is, but it's everything together. So this could be the tip of the iceberg, we'll see how that goes. What are the criteria for evaluating what's good computational math, model or algorithm versus other? So here are some of the things. Some of these are traditional, speed, obviously. We usually count flops, floating point operations. Then we count computational complexity. So multi-grid is, basically if a problem of size n is optimal, right? So if you have O of n, but you can do n log n, that's already pretty good, okay? And of course, computational time. And these are trade-off between them. But today, this is all changed. Flops turns out is probably not the most important. Memory access speed is just as important. How well you can distribute the data and do things in parallel, that's important too. So, but anyway, traditionally, the other one is accuracy. So you can have something very fast, but it may not be accurate. Is that what you want? Okay. Or the other way around. Scalability is another thing. You can do a little problem on your small computer. If you scale it up, then you find out that things don't work, for example. So that's important. I already mentioned about parallelism and communication, memory efficiency. And then the last one is something I put in. What I meant by this is internal, meaning internal to your field. So you can publish a paper. You say, I have this algorithm that is great according to this criteria, but it may have very limited impact to the people who use them. Now, is that good? Well, in the realm of science, maybe it's good. You need to have a lot of these things, and some of these things may work, a few of those. But some of these, for example, for mathematicians, because I live with, after all, I'm speaking to some mathematicians here, right? So the criteria is very simple. You gotta have a proof. Without a proof, I won't even talk to you. Okay? Now, if you look at the practical world, the world is using, there's almost no proof in deep neural network. There's some proof, but they don't apply to the actual application. Are you going to say you don't use it? No, it's proven to work. So I think that's what I mean by internal versus external, I think. All right, here's something I did myself. I'll take it as entertainment. So maybe 7 or 8 years ago, I was wondering, I was still more active in research. I said, what are the 10 most influential papers in computational math? Now, this is according to my definition. It's not on the, but the data I got was from Google Scholar. I just use Google Scholar. So I know most of these, I know all of these people. So I kind of know, in my sense, that these are influential papers from people. So I went to Google Scholar and looked up the citation. I guess I first did it in December 2014. And so that's the first number. The second number, I just did it a few days ago, okay? Very easy to do. Just to give you a sense of comparison. We all know about this book on matrix computation by Golub Van Loon. It has 75,000 citations, but it's a book. It's almost a textbook, so it has more. So it's just to give you a sense. So back in 2014, this paper on compressed sensing, many of you know, had the highest citation. So this is the ranking in those years, and this is the latest, okay, the one I did a few days ago. But for some reason, Donahoe and company stopped listing their papers in Google Scholar. I don't know why. I should ask him, actually. But so I put question mark here, because I don't, these three, I don't know what they are. I cannot find them, okay? But you have a lower bound, right? It's at least this number, okay? Okay. So, but anyway, the next is this paper on level sets by my colleague, Stan Osher. And Sethian is at Berkeley. So, it's increasing significantly. There's this paper on compressed sensing by Candace, Romberg, and Tao. There's referenced a lot, is increasing even faster. Another paper by Stan Osher on total variation denoising. You can see they're going up. This GM-RES, some of you may know, it's kind of conjugate gradient methods. It's used a lot in applications. Then one of my own papers is up there. I was happy to see that. I mean, so anyway, this on segmentation. The famous paper by Dobishi, many of you know, right? That actually, I couldn't believe it. I'm one higher than Dobishi's really historical paper, I would say, in terms of the depth, the mathematical depth. This is higher than mine, for sure. Okay, I can tell you. But anyway, this is internal versus impact, so that's the idea. In fact, I told my student, of all these citations, I probably know at most 1% of the people who cite this, the people. The 99%, I don't know who they are. They don't have to cite me. They don't owe me anything. They cite it because other people cite it, or maybe they find it useful in their work. So it's a very different criteria. It's a very different. Okay, now another benchmark. This is what I said. They are not by peers, but by users. I think that's really, so computational math, you can have that. Again, just for a sense of comparison, especially because I'm in Canada, okay? These two are working in Canada. Like this paper in Nature by the three of them, well, the three Turing Award winners, has 52,000 citations so far. It's a very new paper, relatively new. Compared to this, it's at least 2 or 3 times higher, okay? And Jeff Hinton's paper has over 100,000 citations. So just put this in perspective. By the way, if you have addition or correction to this, let me know. If you know of a paper, let me know. I'll keep on updating this. So I just want to spend a next few slides to talk a little bit about areas that I have worked on myself, okay? So one is computational linear algebra. That's the Householder Symposium that Alan organized. The packages, the methodology is very much focused on matrix factorization. This is, the Golub and Long book is called basically based on this. I myself work on all this. I work on all these methods. Least squares, total least squares. Sparsity that comes in. In the old days was when you do Gaussian elimination, your matrix is sparse. How you deal with that, right? How do you, but today sparsity is a different meaning. It's whether your data is sparse, whether the representation could be sparse. That's the compressed sensing methodology. Iterative methods versus direct methods. And I would say computational linear algebra for a while was kind of saturating, plateauing. Some people were getting out of it because, okay, all the easy problems are solved, all the difficult problems are unsolvable. But then parallel computing came around. So everybody sort of got excited again. And maybe now, deep neural network is machine learning is another new frontier. So many people are working on that. So this goes in cycles. And I think this is healthy in the development of science. New ideas come along. People look at things in a different way. Maybe use old ideas in new light. And sometimes that's how you advance the state of the art. Another area I work on a lot is these multi-scale methods. Okay, it was a really paradigm shift in those days. And I mentioned the Russian influence. I mentioned already. Okay, so in a way, this fast multiple method you may know by Greengard and Rocklin, it was not put into the same PDE framework. It was more analytical expansion of series of representation of functions and so on, but nonetheless, it's multi-scale. That's the idea. Now, another area, and this is something how I switch, or not switch, how I sort of found myself working on image processing. So I started, even in my undergraduate days, I took a class on CFD. It stands for Computational Fluid Dynamics. I was at Caltech, which is like, a mecca for this kind of thing, right? JPL and fluid dynamics and so on. I took a class. I thought, this is pretty interesting. It's something useful. I understand. You have Navier-Stokes equation, and then you can actually get results. In fact, there's a little personal history there. I actually have a degree, a master's degree in aeronautical engineering. I don't tell people that, okay? But it's because I'm interested in airplanes. So Caltech, JPL, von Karman, all that stuff, I thought this is where I really learned how airplanes are done, right? So I took all the classes. By the time I graduated, I knew nothing. I knew nothing about how airplanes work or rockets work. Because Caltech's education is very foundational. You learn all the equations. I never saw an airplane. Anyway, even on the blackboard, nobody drew an airplane. So when I graduated, I asked the professor when I was a graduate, I said, well, I'm interested in this. What should I do, So I keep on learning equations. He said, well, Tony, there's a new tool called computers. And we use computer to design airplanes now, more than we use wind tunnels. And what they meant was the 747. That was the first airplane that is using more computer simulation than using wind tunnel. And I, as a student, I used the wind tunnel. I was a staff member to do the wind tunnel. So I know what they meant. I said, wow, if that's the case, I'm going to study this new thing. Where can I study it? Well, Caltech did not have computer science department. They didn't want me to stay in the same university, which I think is wise advice, okay? So they said, well, there's this new university up north. We heard they're pretty good. It's called Stanford. I said, okay, maybe I'll give it a try. This is how Caltech looks at Stanford, okay? This is a true story, okay? So that's how I got into computer science. So I grew up with CFD. So years later, I was at UCLA, working on my research, and my next door neighbor was Stan Osher. So, he's as far as you can get from numerical linear algebra. He didn't know, he couldn't care less about, numerical linear algebra. Really, he's a PDE guy, conservation law. And one day he came to my office and said, Tony, I want to know about Lanczos method. I said, what do you mean? Well, because he's working on image processing, and it involves certain optimization. It involves certain I said, wow, if Stan Osher is interested in this, there might be something in that I can do in what he was doing, which is image processing. And that was one of the papers that had, in the top 10 papers. So that's how I got into it, just by accident. Now, why was CFD so popular in applied math, in computational math? Because it's like it's a difficult problem, so it doesn't go out of fashion. Okay, you cannot really solve it, but it's enticing enough. You can do something like what I said, but it's so difficult that no matter what you do, you can bring something to it. I think that's why it's enticing. So, for example, it's multi-dimensional, well, obviously, multi-component. You have different component of your velocity, pressure, whatever, or energy, all that. It's multi-scale. You look at turbulence; it's still unsolved today. Okay, multi-scale. It's nonlinear by definition, so all the linear method go out the window. Okay, it has discontinuities like shock waves, very difficult for numerical methods. So all this stuff. By the way, all this stuff it turns out is in image processing. That's how Stan Osher got into it. So he was asked by his co-author Lenny Rudin. Okay, he was working at Caltech. He drove down to UCLA. So he was asking Stan, I know you are good in discontinuities. I have discontinuities. Can I pick your brain? That's how they got to work together. So for Stan Osher, it was shock waves. So all his career was developing numerical methods that are stable and accurate and don't have overshoots and so on. That's exactly what they needed in image processing. So image processing, in some sense, is the new CFD. That's how I see it. So I don't know what the next thing is. Maybe the brain is something. How do you model the brain? That's very difficult. Okay, so this is a little bit of when I started on this. Let me skip this part. Oh, I have to say a word about this. SIAM now has a journal on imaging science. So I wrote a proposal for that journal. It was 2006. And Kirk Jordan, some of you may know, he worked at IBM. So this is a proposal for a new SIAM journal on imaging science that I submitted to SIAM. But this is my own handwriting. Anyway, SIAM was quite conservative in forming a new journal. How do you form a new journal? What's the business case? That's really what they want to know. Are we going to earn money or lose money? Will there be readers? In fact, the idea at that time was SIAM never had a journal based on an application area. I never knew that. SIAM, SIAM journal on numerical linear algebra, SIAM journal on PDE, SIAM journal on whatever it is. It's based on techniques. It's very much an internal kind of journal, right? It's the tools that we use. Whereas now, today, you have many. Imaging science was the first. Today, you have many different things. They were had not done it before, so they were questioning it. But anyway, I did not end up editing this journal for other reasons. I can tell some of you later. Let's skip this. I just want to mention here IEEE, transaction and image processing. Okay, when I started, I submitted my first paper to I think NSF in using PDE for image processing. It was rejected outright because the reviewers say images are discrete. How can you use a continuous model like PDE? Reject. That was it. Okay. So I said, wow, I had no idea. I did not anticipate that perspective. I said, well, maybe they're right. I have to explain my case. Today, you don't have to. So there's a burden of being the pioneer because people don't understand what you're doing. So this is the first special issue of the IEEE transactional and image processing. Before that, there was no continuous model in this journal. So that's why the SIAM journal was formed. I mean, I think I had 2 papers in here. Here's one, I forgot. Here's another. This is a typical textbook back then. It's very different. If you look at image segmentation, you look at point, line, and edges. Here you use a level sets. You use a differential geometry to model objects and discontinuity. Completely different approach. I started at 2, right? Okay, I'm still safe. Okay, thank you. Okay, what about image processing and applied math, right? Or computational math, that's what I really want to say. So these are the mathematical techniques that come into play. It depends on what you do, you know. You can see that including wavelengths, total variation, and so on. In a way, this is going from math to the image processing. You have mathematical tools. You see what can be applied to bear on image processing, okay? But it doesn't go only one way. Very often from here, you can feed back into here. That's a healthy state. So for example, these things, a lot of them are going that way, okay? I mean, I can't go into technical detail. There are certain things in there. For example, there are things that people develop over here. It didn't really work so dramatically well, but they found that when you apply to the context of image processing, they work spectacularly. Then you start realizing why. Why is the case? Then you realize, you study it, and say, oh, that's why. So then you put it back, and you can use it on this side. So that's the kind of healthy iteration that is used. For example, one I don't want to get into technical details. I work on this a little bit. It's for optimization, okay? So there are many optimization problems that don't have a unique local minimum. Okay? There are many local minima and all that, right? So it's very difficult. So, but it turns out for a certain optimization problem in geometry. So for example, how you identify an object in an image. You can set it up as a variational problem, you can optimize. Well, it turns out for geometry, very often you can take a problem that has no unique local minimum, but you can convexify it. You can embed it into a higher dimensional problem, then you have a unique local minimum, which is a miracle. And you then solve that problem using any good old techniques. And then you can then take the solution and then map it back to your original problem. If I told my student, I said, boy, this cannot be true universally. If it were true, I'm sure it would win the Nobel Prize, right? Any optimization, you can get the global minimum or optimum, no way. So a certain problem, you can do it. And that's something that we learn by looking into this image processing optimization problem. I suspect in deep neural network, there's something like that going on, okay? So anyway, we'll see. Compressed sensing is one example of that. I assume you have some familiarity with it. Sparsity, as I explained. So sparsity means you have a vector, how many are non-zero? How many entries are non-zero? That's really what it means. The vector is the representation of the signal in certain bases. That's the idea. So sparse, meaning the smallest number, right, of non-zero. So basically, you use what's called the L0 norm. L0 is, if it's non-zero, then it's 1, 0 is 0, right? It counts, basically. But L0 is non-convex. It's very difficult to minimize. So somebody realized that you can convexify it by using L1. So L1 is the closest to L0 that is just convex. But it turns out that one often gives you the answer you want. It's another miracle, okay? That's the miracle of compressed sensing. And randomness comes in here, okay? So the idea is compressed sensing is where the word says when you sense, like when you take a camera, you take a picture, you don't just sample the pixels that in your field, okay? You take a convolution of the field. You take an average of the field, and you randomize that. If you randomize it appropriately, you have captured independent information in those random averages. That's the idea. And it turns out you can take only a few of these random convolution and you can get the exact answer. This is actually a very interesting concept. So for example, in principle, you can buy a camera with only 1 pixel. You know, right now you buy it, right? They tell you, whatever, the more pixel, the more you pay. But in principle, you only need one pixel. You just take many convolutions. In fact, I think some people were trying to build a camera like that. I know a commercial is not successful, but you could do that. So the idea is that randomness comes into it. In fact, this property, which is in their paper, is the key to proving that this method can actually get you the exact answer. So the randomness is very important. You get exact recovery, okay? So I want to tell you a personal example of how I myself work into this. Without going into the technical, this is one of the 2 equations I show. So the idea is that if I show you this picture, right? Actually, this picture is a real picture in JPEG, but I take, I don't know, 50% of the coefficient and I zero them out. So let's say I lose them in transmission or get corrupted or so on. You cannot recognize who that is, right? So that's the idea. So the question is, when you're given that image, can you recover as much as possible the original image, okay? Now, in compressed sensing theory, if it's sparse, in principle, if you take enough sample, you can recover the original picture. Now, this case is not like that. It's not exactly sparse. But anyway, you can set it up like an optimization problem. Basically, you say, how do I fill out those 0 coefficient, the wavelet coefficient, such that I control the regularity of the resulting image. The regularity here is defined by TB norm. Very, very elegant, actually. No parameters. This thing has no user tweak parameters. Okay? So just put them in as much as possible so the resulting picture is as regular as possible. Very elegant. There's a model for this where you have noisy. You can also denoise at the same time, but forget about this for the time being. So here's the result, okay? So here's the original image you can recognize. So here's the thing that we recover. You see the signal to noise ratio is actually quite substantially better than, right, compared to this. It's almost a 9, 8 over this. And you see here is a contrived, artificial image. Here is the also 50% screw up. And then you see here, you actually recover the original thing with very sharp edges. You don't have Gibbs phenomena. You don't have things that are moving around. So when you look at this, you start to wonder, what's happening here, okay? So here's the case that we did with my student. So look at the picture first. You take this little blocky image. You take out, I don't know, 50% of the coefficient, whatever it is. You get this image. You use that method, you get this back. So this is exactly that. This is exact recovery. I didn't know that. We didn't know that. So we did this. Here's the edge, exactly sharp, okay? But that turns out to be a preview of compressed sensing. We did it. We were not good enough mathematicians or physicists to realize that there's a theorem in here that you can prove. We didn't know that. So they deserve a lot of credit for doing this. Forget about this. So this is, basically it says compressed sensing is doing exactly that. That's the idea. Okay, so this slide I think is useful. I think you are in this field, right? Maybe others. So there are connections between the old and the new. That's the point, okay? So on the left are some of the old optimization methods. For those of you working on that, you recognize these. On the right are the new terms that the image processing people who do optimization give the term. And there was kind of disconnect. And then later on you said that it's the same. Many of these methods. For example, here's something called Bregman method, Bregman iteration that my colleague Stan also used. Well, it turns out it's augmented Lagrangian. So he realized that that's the case. But it works extremely well in the TV case when you have discontinuities. It doesn't work as spectacularly well when you do it for PDEs with continuous thing. So it was, in the old case, it was one of the many methods that were used. But in the image processing case, it was the best method. So this is something that we did not anticipate. Here's something for those who do optimization. You see, for example, it's very difficult to do second order methods or higher or superlinear method for conversion, even in neural networks. Now most of the methods are linear or even sublinear, okay? Because the problem is so big. You cannot store Hessian, for example. But people are looking into that now, if I understand. Because the problem is so big, if you do a sublinear method, it just takes forever. You need a supercomputer. You need a farm of GPUs to do them. So I think there's some room for some ingenuity here to develop faster methods. All right, here's my favorite slide, okay? This is my own, I'm sticking my neck out, okay? This is a lesson that I have learned in my career in this, okay? So I'll share with you, so take it with a grain of salt. One is having the right model is more important than having the fast algorithm. I lived through this myself, because I was working on fast algorithm myself, right? So I was not responsible for coming up with the model. And especially when you have CFD, the model was done for a century. So what am I going to do, right, to do that? So, but in image processing, the model was evolving. Quickly I realized, if you develop a fast method for the wrong model, it doesn't advance the field. And the field was just evolving that model. So I figured, I might as well develop the best model. So I became more a physicist of images, if you will. And I think that applies to many of us. Because in a way, in our field, it's like you have a hammer, you're looking for the nail, right? So that often does not work if you take it to a high level, okay, of science. That's one lesson I've learned. By the way, I showed my student these lessons, okay? So simplicity trumps everything else, okay? What do I mean by that? Well, some of us, we pride ourselves in having complicated things that we can solve. This is how we get papers published, right? It's kind of macho math. I can do it, you can't. Okay, that's really what it is. Well, if you can, that means the user cannot. They will not use your method. So your impact is lessened just because you cannot. People don't know how to use it. So my paper on, one of my top 10 papers, right, that method on segmentation, is because it's extremely simple. Anybody who has any science background will be able to implement it. That's why you have 15,000 citations, because most of the people are not mathematicians, okay? They could be medical doctors. They could be people in their various fields. So simplicity is very important. Now, it has to work. It has to work, okay? Just cannot be just simple. There's not enough. Proof, of course, I lived in the math world. Proof in the math world is sacrosanct. If you don't have proof, you don't belong in the math department. Okay? Computer scientists, you probably appreciate that. Okay? So, okay. You are in the faculty of math, right? So I realized. But I think in Waterloo, I don't think you have to prove yourself, in that sense. But proof is good, but not absolutely necessary in the real world. Because we're using, many of the stuff we're using every day in our cell phone, in talking on the phone, they don't have proofs. But good idea is a must. You must have a good, the good idea comes, first of all, from insight. Second is serendipity. Sometimes people stumble into things that work, or try and error. They bang their head onto a problem, and then they know what doesn't work, and then they figure out a way to work. Okay, that's very important. Well, I mentioned this in my previous slide. Old methods can find new use. So it's still good to teach a student the old methods. Okay, so because like optimization is a good example. New application can inspire new computational math. Image processing was one of them. Okay, that's a new application, but it's not just throwing over the fence, the method that you know. It comes back to help you. And that's how the field grow in a healthy way. Hardware changes, good ideas last. I work on hypercubes connection machine. I actually program on those. They're long gone. Most of the people in the room never heard of them, okay? But the good ideas that come from that actually is still used today. So I think there's also a lesson there. Another one is very common to people working in the math idea. That is, the ideas that you've developed for one problem, let's say CFD, can be used for other problems. Like, who would have guessed that shock capturing methods can be used for doing imaging? I mean, even Stan Osha didn't know that, right? You had Lenny Rudin who came down, drove down the highway, and asked him that question. That's really the idea. Number 8 is what appears different may be related. So many of these methods in PDE or graph modeling, we're seeing it, they use different languages, okay? Well, you heard there's one that connects the two. Laplacian, right, is a PDE method, right? Laplacian. Well, you have graph Laplacian. You define on edges. Well, it turns out they're very much the same. You can have Laplacian related to heat equation, right, which is diffusion. Well, you have diffusion on graphs. So the idea actually is used a lot. So it feeds on each other. So I think that is something, I think we should teach our students this kind of stuff. That's what I'm saying. New math plus old tricks often advance the field. So, for example, I wish I knew more, had learned more differential geometry, okay? It turns out that if you add differential geometry with, let's say, augmented Lagrangian methods, which is a method, you can actually, like in image processing, it really advances the field. So people were working on one and not the other, okay? So if you combine them, if you're at the right place at the right time, and you have the right insight, you can really advance the field. And last but not least, is be the first to spot a math idea or a rich application. Otherwise, you're only a follower. But you have to take risk. Because you can spend 2 years, 3 years banging your head, you may not get anywhere. And especially in engineering, because I work in both. You really have to go to a meeting every 3 months. You have to go to a meeting every 3 months and show that you are 5% better than the last time you talked about it. The pressure is there, okay? So you have to take risk. Okay, so you cannot put all your eggs in one basket, otherwise you cannot get your next grant, you don't get your next graduate student to work with you. What are you gonna do? So anyway, that's my 10 lessons, okay? Last couple of slides. Teaching of computational math. What should we teach our students? What are the important things to include? Traditional, you look at any textbook, yeah, this stuff. Okay, you look at any numerical. But what about these other stuff? They are not so common in any books on computational math or numerical analysis. I think they should be, okay? You need more math. Like I said, I wish I had learned more math. In fact, when I was a student in computer science, the student do not know any fundamental math. In fact, it's almost, we all joked that if you don't like calculus, you become a doctor. That's what math students would say. Well, it applies to computer science too. If you're interested in continuous math, you don't study computer science. I told that story before. But they should know a little bit about application domains. It should be a broad education. It's actually part of liberal arts. Liberal arts is not just about studying non-science and science, right? It's also, even within science, you should be liberal. That's what I mean. You should teach not just techniques. You should teach thinking. I think that's really the key. Okay. What about the future? Plenty of challenges. I don't think we'll run out of problems. Okay. Biology is a big field challenge. Biology is not suited to mathematical modeling per se. It's what people think, because systems evolve through evolution. It's difficult to write down things like Einstein's equation or Maxwell's equation, although I think Darwin's law is pretty good. And then you have DNA now. It's more discrete, right? But biology, I think, is one of the big frontiers. Big data, I don't have to tell you, uncertainties, and so on. So these are some of the ideas. So just to close, so in my own field, there are people now going in this direction I just mentioned, the future. So I just want to highlight two. I'm not a collaborator with them, and so on. One is George Kaniadakis at Brown. So he's combining machine learning with sort of traditional multi-scale multi-physics problem, okay? So you can imagine, you still use Navier-Stokes, but you use data, and machine learning. You put them together, okay? So that's one. He has many things online that you can read about. Another one is Weinan at Princeton, and he's going in a big way into using machine learning in material science and so on and so forth. So here are two, I would say they're leaders, even in traditional computational math, they are leading the way to explore the frontier. I think we need leaders like this. Go on. No, I don't have time, okay? So I just want to highlight this thing for you. That is, back in 2003, almost 20 years ago, I was asked by the Carnegie Initiative I was one of two people they asked. The other one's Hyman Bass at Columbia. Those of you in math, you know. To write something on the PhD, the doctorate. What can be changed? So this is the article I wrote. Okay, you can get online. It's in the notices of the AMS in May 2003. So I wrote this. In fact, when I was preparing this talk, I went back and looked at it. I am proud that I wrote this, but nobody pay attention to this. Okay, so you know, none of the thing I said has changed anything. Okay, but I'm still glad that I wrote it. Okay, so you can. So here's this thing. You can look at it. I don't have time. Thank you very much. Yeah.
Okay, we have time for questions, so open the floor here. We also have the online version. If anybody wants to ask a question online, you can put it in the Q&A. There, go ahead, Mark.
It struck me, I think it was...
You have to use the microphone, because otherwise it won't go out over the side.
It struck me, I think it was slide 10. You had a list of papers.
Yeah.
And the first 10 were sort of, I think, a lot of them came out of compressed sensing, Donahoe and Canvas Verstel. And these were, I would define many of them as sort of the definitive mathematical results that describe methods.
Yes.
Maybe that's too simplistic, but
yeah, it's my personal list.
Compressed sensing, I mean, we knew about L1 optimization before we had RIP and things like that.
Yeah, right.
Below the line,
yes,
we have the deep learning, the hidden classification, which don't have the proofs. They're not, in a sense, they're the definitive papers, but they're not the definitive math papers.
Right.
I'm wondering what it says about sort of maybe there's a set of papers before this one that we're not seeing, or a set of papers after these ones at the bottom that we will be seeing.
Well,
and what's the interaction between
good question.
Heuristics and proofs and
good question. Let me explain why I included these papers. So I happen to know all the authors, and I remember it was like deep learning back then. Okay, all of a sudden this compressed, sensing idea came. In fact, Candace gave a talk at UCLA Math, at IPAM actually. So everyone was like, wow, this is a miracle. And then everybody was jumping in. Medical field, people in electrical engineering, mathematicians. So it's a little bit like deep learning today. So these papers were getting phenomenal citation. So that's why I knew they are very influential. They had great impact. That's why I included them. I included them not because they have proofs, okay? But actually, you're right. Many of them do have proofs, but not this method, not Osher's method. I mean, this one has some proof, but it's not the essential thing. My paper doesn't really have proofs, okay? So it's not because of that. Now, of course, today with the internet, with Google Scholar, okay, these papers, first of all, many people know about them, first of all, so they are cited more, but because they really have wide impact. I mean, there's almost no area of science where machine learning or deep learning is not used. So it's a different, but in a way, these are the predecessors. Now, I know enough about the field and the people that there was nothing before them, really. For example, I know like this level set stuff. Level set, of course, is not new, but to use in this way, as an implicit method to capture interfaces was due to them. So it was kind of a small revolution. So I think exactly it's the idea. Somehow the methodology was there. They were able to, they have some insight. They put it together and have a simple method to describe it and to implement. So anybody can use them. That really is the key. So in a way, it's closer to engineering, if you will. They didn't just prove a beautiful theorem and just leave it on the table. They actually show how you can use it to solve your problem. That's how I see it. By the way, I agree with you. I hope too soon to follow will be some deeper theorems and theory for these. But in this field, the field is driven so much by the impact. Right? When you go to a conference, you go to ICML, if you show your ultimate theorem, of course you get a lot of respect, okay? But you just prove a theorem that is not central. They want to know, what are you bringing to the table? How can you advance? I can model this. The result is this. What can you do? What can your theorem do? It's brutal, actually. Maybe unfair too, but that's how it works.
I just have a follow-up question on that. But these are a little bit, we were comparing apples and oranges, are you not? Like the publishing in computational math is quite different than publishing in machine learning.
No,
for example, like
you're
if
right.
a paper in sociology, let's say,
Yeah,
with
yeah.
300 citations is a huge paper, right?
No, my emphasis, these are computational math. This is just for reference. In other words, the order of magnitude. I'm saying we should be modest here. That's what I'm saying. Of course, if you go to pure mathematics, the citation number is one order of magnitude smaller. So, so not many people can read the paper. So, by the way, it doesn't take anything away from the importance. So I think here you have, because as I said, you have many users who are citing it. But here you have many, many more users. It affects all areas of science. So that's the perspective.
Other questions? I have another question. Maybe, so computational fluid, CFD, computational fluid
Yes.
dynamics, right? So can you speak just briefly about how computational math is impacting the study of the changing climate?
That's a good question. Well, we get weather forecasts on the TV channels, right? If you're old enough, you remember back then, the forecast was not that good, okay? But today, you can trust it a lot more. I do anyway. It's really quite amazing. A lot of it has to do with the models, the physical model, understanding of the physical processes, but also the simulation. They can really do a great job. And weather forecasting, and more generally climate forecasting for a longer period of time, is really advanced by a combination of disciplines. Obviously, meteorology, physics, chemistry, and so on, but also simulation. These supercomputers of the world, one of the big uses is this. In fact, one of the use that at COWS we want to use our supercomputer is to do climate modeling for the Middle East region. Because basically, there are about maybe 5 global weather forecasting models. US has one, Europe has one, Japan has one, China has one, probably there's another one. So there are 5 of these. And they don't agree. Most of the time they don't agree. Because I visited some of these stations. So some people build their own thing, or they take some average, or they use some human. But because they use different, they may even start with the same model, but they use different data, and they have different algorithms do it. And as you see this stochastic or chaotic behavior, because weather forecasting is actually the origin of the theory of chaos. This Lorentz, the 3-body problem, come from meteorology, basically. You just take 3 degrees of freedom, and it becomes chaotic. So if you're trying to model the whole world, it's chaotic by definition. So it's a very difficult problem. But it's come a long way. The forecast is really doing fantastic, actually, I think. Try it next time you look at the model. They're really very, very good.
But when you look at the longer term predictions, I think you just mentioned this, that the range of forecasts of where the global temperature is going to be in 50 years are absolutely astronomically different. I mean, you can get predictions of plus 50 degrees and predictions of minus 4 degrees.
So if you follow the IPCC, whatever, the model, well, this whole climate change thing that people are going on, right? They want to keep the temperature rise to be less than 2 degrees, I think. So how do they do that? Because they are based on modeling and simulation. So even though the different models have variation, the band shows where it's going. I think that's my understanding, okay? So, well, there are a lot of skeptics, as you know. People don't believe in global warming or climate change. I think generally the scientists knows the stochastic nature, but within that band, they know that's what's going to happen. And how do you convince people? You have to convince them that your methodology is credible. One way is to look at your weather forecast today. They're actually very, very accurate.
Any more questions? Oh, yeah, go ahead.
So you have Hello. Yes. So I would like to know, you have say 2 algorithms. One is very exciting, clever, genius, but it has very less implication in the real world. And another one algorithm is not that much clever or very exciting algorithm, but it has good impact in the implementation level or impact. just for example, say Fermat's last theorem.
Fermat's last theorem, yeah.
Yeah, it's like one of the top millennial problems. Then you have Poincare conjectures and others. So these problems may or may not have implications, big implications, but still the proof, if anybody finds the proof, they get big prize. At the same time, there are
You're not going to ask me to choose.
learning. They have good implications and others. So what's your thought on that?
No, so I'm a big believer in basic science. You know, I was head of the NSF MPS. People look at particle physics. People look at the sky astronomy. I think the world is full of examples of where you look at basic science. We need the world's best brain. You don't need a lot of people. You only need the best brain to look at those, okay? I always quote an example. I have another talk, which is titled, "What's math got to do with it?" So for example, what does math got to do with your GPS? You ask your friends. I asked my daughter when she was a teenager. She said, well, it's like the radio, right? I turn on the radio, it tells me where I am. Most people think that way. So the GPS, as we know it now, I mean, now it's much more refined, if we know it back then, is based on Einstein's equation of relativity, okay? And also the atomic clock, the development of the atomic clock. Well, people say, really? So you can explain, so what's math got to do with it? So you cannot ask Apple or Sony to develop Einstein's theory of relativity just because you want to develop a GPS. It's impossible, okay? That's how science advances. So we need people to do that, no doubt. I'm just saying, you know, my lessons is if you're working in my own little narrow field, you just have to keep that. So I have a lot of respect to physicists and mathematicians. The world needs them, yeah. But you don't want to just produce your run-of-the-mill, okay? Just to say I have a theorem. That's not good enough, you see what I mean? You gotta, there's internal versus external. No question from this side. Yes, but you had one there, sorry, you had one. Yeah.
Okay.
There's one back there. I gotta earn my dinner tonight, you know? So
Hello. I have just a question. I don't know how to ask. So you have said something about old paradigm and then the new paradigm. I think there's one thing you missed, that is in the old paradigm. In the research, people think that many things are smooth, and then because of the compressed sensing, and then the modern paradigm is about non-smooth. For example, L1, L0 are not differentiable, singularity, and which is very different from the old school of thought. For example, all the CG method, multi-grid, they work on smooth function, that kind of thing. So my research is actually trying to combine two things. That is, for let's say I'm working on combining multi-grid, that is a thing that is famous for solving smooth differential equation, assuming the stuff is smooth. And then right now in machine learning or optimization, people working on non-smooth thing, that is, for example, forward-backward method or proximal gradient. So actually, I'm now trying to fuse them. And to be honest, I face a lot of challenge because it's not very easy to fuse things. So my question is, how do you deal with this kind of thing? Because I'm just a very beginning level researcher, so maybe I don't have enough experience, but I just find a lot of frustration because it's quite hard.
you don't want to solve an easy problem, right? Because then there's no impact. So that by itself is not a reason not to look into it. Well, I mentioned about smooth and non-smooth. In fact, as I said, some of the methods developed here, they were applied to smooth problems, and it turns out they were okay, they were good, but they are not outstanding. So it's just one of many methods. But when you apply to non-smooth, it turns out they were spectacular. So people look into this and say, why? And it turns out that is a good method. So in fact, I think there's a way to look at why L1 is good. If you look at the L1 norm, it's like a little, you just in two dimensions, right? The L1 equal norm is like a little square on the side. And you move something like this, you hit the peak of that thing, and that is the exact solution. So nobody looked at it that way before. I mean, this is a simple explanation. So there's a reason, theoretical reason, why this non-smooth thing with the L1 applied to it actually works. So that's the insight. Once you have that, you can apply to other things, material science, all kinds of stuff. So that I suggest that's what you should look at. Look at what makes the non-smooth thing works well, and you want to combine it with the smooth things, right? So the smooth thing is where you can have fast convergence, for example, right? You can use second order methods. You use Newton, basically. But the non-smooth, you cannot. So you have to find a way. For example, you can alternate between them. That's often what people use. One step using the smooth one, another step using the non-smooth one. So for example, that's one method. Have you tried that, for example? But anyway, that's the idea, okay? Now, if you can do that, if you can combine the best of the smooth with the best non-smooth, then you really have something going, okay?
Okay, last chance.
Okay.
Okay, let's thank President Chan again.
Well, thank you very much.